Um, Hello, everybody. And today, in the next about 30 minutes, I'm going to be speaking about my experience in porting Mender to new i.MX device. This is the Toradex Verdin i.MX 8M Plus. Although this is a product showcase for both Mender and Toradex, I'm not working for neither of these companies. And this is going to be quite of a technical talk because I will share my experience and the practical problems and things that I have done in terms of upstream contributions. I work for Konsulko Group. This is a services company specializing in embedded Linux and open source software. The company provides us hardware, software, build, design, development, and training services. Konsulko Group is based in San Jose, California, but we have engineering presence worldwide. And actually, I'm speaking and working remotely from my hometown, Plovdiv, Bulgaria. My colleagues and I have numerous upstream contributions to a lot of different projects, and I am focused on Yocto Project and Open Embedded. I have some contributions over the years through various meta layers. The agenda today is, of course, about Mender. Initially, we're going to talk about briefly about software over-the-air updates, Mender, and the integration of Mender on new hardware devices. There is going to be a practical example with Toradex Verdin i.MX 8M Plus. And finally, we'll wrap it up with conclusions. Hopefully, there will be a few minutes left at the end for Q&A. So there are several different embedded Linux update strategies. We can do A/B updates where we have A partition, B partition, two identical partitions basically, and the bootloader is switching between them. This is going to be the main focus of this talk. It is possible to have delta updates. This means that we can have binary diff of the differences of the file systems and provide smaller updates. It's also possible to use containers, just like they are used in the cloud. Nowadays, there are very powerful embedded devices which fully support containers, so containers is another strategy. And of course, because each of the three strategies that I've mentioned have advantages and disadvantages, sometimes it makes sense to combine them. And actually, nowadays, it's quite often to combine different strategies together. The talk is about Mender, but are there any other open source alternatives? And the answer is yes, absolutely. There are a lot of them. Actually, I have delivered several talks about Rauk, which is another A/B software update mechanism. As part of my job at Konsulko Group, I have been involved in the past in the integration of libostree, which back then was known as ostree, in a layer called meta-updater using actualizer. Nowadays, there's actualizer Lite as well. All these solutions based on libostree are using binary delta diffs to do software updates. Even Toradex is maintaining their own solution for software updates called Horizon, which, as far as I know, is based on libostree as well. So yeah, there are a lot of different options. And with the combined strategy, we can combine different solutions. For example, we can use containers for updating applications, and we can combine it with A/B updates of the base Linux distribution. There are cases where we can do A/B updates combined with delta updates. And actually, this is what Mender is capable for. This is one of the advantages of Mender. So what's so special about Mender? Well, Mender is an open source update, I would say, turnkey end-to-end solution for embedded Linux devices, because unlike most of the other solutions that I've briefly mentioned, Mender is not just the client that runs on the embedded device, but it's also the whole infrastructure and the backend services to manage not only a single device, but a fleet of devices. Mender is available as a free open source or paid commercial enterprise plan. However, in this talk, I will be talking about primarily, and I would even say mostly, about the open source version of Mender. I'll just briefly show a few specific things related to the Delta updates, which are paid commercial plan. So the AB update scheme of Mender is fully open source, and this is what we will be using today for the majority of the slides. The source code of Mender is available in GitHub under Apache 2.0 license. Of course, Mender is compatible with the Yocto project. That's why we are here today, to talk about the Yocto project and Open Embedded. However, Mender is also compatible with binary operating system images of Debian and Debian derivative Linux distributions. So you have the option, even if you're not using Yocto, to use Mender. There's a huge list of supported devices by Mender. They are available in the Yocto Open Embedded layer meta-mender community. Here is a short list of some of the most popular. Of course, Raspberry Pi, BeagleBone. It's possible to run Mender on Intel x86-64 devices. It's also possible to run it on Rockchip OWinner devices and NXP. Today, we'll be focusing on NXP, of course. There are many more. Have a look at the meta-mender community layer and the list of sub-layers there for each supported device, depending on the Yocto release that you are targeting. So this is a very typical Mender partition layout. And actually, it's typical not only for Mender, but for pretty much any solution for performing AB updates. We have the bootloader and two identical partitions. For simplicity, one of the partitions is called A and the other partition is called B. So the updates are installed on the inactive partition, and after that, on reboot, the bootloader should switch to it, and the partition to which we have installed the image should become active. Although in theory, it's possible to perform updates without keeping some persistent data. In practice, this is not very convenient, of course, because you always need some kind of a configuration or something to be stored on the device between software updates. And because of this, we need a persistent data partition. Actually, this is something important for Mender because Mender stores its own configurations on this persistent data as well. One more thing, as you have seen on the figure, by the way, this figure is taken from the Mender documentation. If you want to perform not only root file system updates, but also kernel, the kernel must be part of these partitions where we perform the updates of the A and B partitions, and the bootloader should be looking for the kernel there. Of course, the most important thing to perform successful upgrade after installing it is the bootloader, because the bootloader is responsible for switching between the A and B partitions. And Mender supports both group and U-boot. By default, it's recommended to use group, but also U-boot integration is available for ARM systems. So if for one reason or another you're porting Mender to a new device where you cannot use group, U-boot is also an option. Mender works with Intel devices. This is a little bit of an off topic because of course the primary focus here is on i.MX 8, but it's also possible to use Mender with Intel x86-64 devices. This support was added in 2018. Actually, as part of my work at Konsulko Group, I have used it on several occasions. And here is an example of upstream contribution based on a bug fix that I did for Mender running on an Intel device. Now, let's talk a little bit in more details about the Mender data partition. So this is the partition which is preserved across updates. The information stored in this partition remains intact no matter how many updates you do. That's the idea. So Mender creates /data partition and stores all the persistent data there. So if you have a specific application that should write data at runtime, and this data should remain after upgrading. Make sure that this application is using the right partition. And the Mender client application that is running on the embedded device actually also uses the data partition, because it stores some configurations and status in /data/mender. There is a variable called mender data part size megabytes, which configures the size of the data partition. By default, it's 128 megabytes, but of course, by changing this variable, you can set it to a different value. It is also possible, if the Mender feature Mender Grow FS data is enabled, to resize the data partition to the available space on first boot of the system. This Mender feature is actually relying on the systemd Grow FS service. Another interesting thing that I had to do on several occasions in my practical experience with Mender is to create a data partition in advance and to put specific information on it so that it will be available right after the installation. And this is also possible to be done. So basically, BitBake will create the data partition for us if we add to the image FS types the data image. Mender data partition supports several file systems. There are different devices, different use cases, so you may need to switch to one of them. By default, it's X4, but ButterFS and F2FS are supported. Actually, I was the one who added the F2FS support. This is a relatively new feature for Mender, and I had to do it because on a specific device, this file system was providing a significantly better performance, and I did this upstream contribution of this small new feature to Mender. The Mender client, this is the application that is running on the embedded device, and the Mender client supports two client modes, managed and standalone. The managed mode is the default mode. The client is running as a daemon and pulls from the server for updates. The standalone mode is more appropriate for doing upgrades with physical media like a USB stick, or any network update in pull mode, even when manually installing an update. Actually, the standalone mode is quite convenient for development purposes while porting Mender to new devices. So in order to use the Mender client in standalone mode, the systemd service for Mender should be disabled, and on the machine in the same network where the Mender artifacts are, we have to start a web server. Here's an example how I'm starting a very simple HTTP server using Python 3. And after that, on the embedded device, we need to log in and execute the Mender install command, followed by the URL to where the Mender artifact is. This is the Mender artifact with which the update is performed. One more interesting thing about the Mender client is that at the moment it's written in Go, but I recently read the news that there are plans to rewrite it in C++ because Mender is having in mind targeting real-time operating systems. So now let's have a look at the Mender update workflow from the perspective of the embedded device. There are 3 steps to actually successfully install a Mender AB update on this device. First, we need to apply the update. This means that we need to download the update and flash it on the inactive partition. For example, if you are running from A partition, we need to download and install this update on the B partition. For example, this command here is exactly this first step. After that, we need to reboot the device. This is something important to be said. So in order to apply the update, Mender requires a reboot because the bootloader is going to switch the partitions. So unless we do a reboot, the update won't be applied. After doing the update, if something fails, the bootloader will switch and boot again the other partition. However, if everything is okay, the bootloader will boot the partition on which we have installed the update. We have to inspect this this update to make sure that the image is working fine on the device. There are options how to do this automatically, and if everything is okay, we must accept the update by basically doing a mender commit. And once we do a mender commit, this means that this update is successful, and each time on next reboot, the bootloader will load it. However, if something goes wrong and we don't do a commit, then the bootloader will roll back to the previous partition on the next reboot. Mender has some really cool features. For example, we have the option to do Mender single file artifact. This is a deployment of a single file directory or even a container image for application updates. This is pretty convenient because sometimes you prepare an update artifact, you install it on the devices, and next moment you realize that some configurations are wrong, and these configurations are just a few lines of code, so you don't necessarily need to update, to perform a whole update that can take a lot of space. You can just deliver this single file and fix the problem. Mender also supports several add-ons. There's an add-on for remote terminal, for file transfer, for port forwarding, and for configuring. As I said, Mender is a kind of a end-to-end solution, and in many use cases, it's a turnkey solution because it's not just an update client that runs on the embedded device. It's far more than this. There are these add-ons. There is the backend for managing the devices. So it's a complete solution. And now, let me spend just a little bit of time talking about the Mender Delta updates. This is a robust update of the rootfs, but it's only available with the commercial Mender plan. So it's a closed source implementation. It's not open source. Again, it requires a reboot to apply the update. Again, it supports rollbacks. So it comes in conjunction with the AB updates. So you have the AB updates, which are part of the open source implementation of Mender. And on top of them, you have Delta updates. There is a tool called Mender Binary Delta, which creates the artifact by comparing the two Mender versions for the AB updates. A very important requirement is that Mender Delta updates require read-only root file system. And in terms of Yocto and Open Embedded, there are convenient ways how to switch your image to read-only rootfs. If I remember correctly, yesterday during Scam presentation, he mentioned this as this feature of Yocto and Open Embedded among the less known features. Well, here's a real-life example where we need the read-only rootfs feature. It could be added as an image feature into the image recipe, or alternatively through local.conf. So beware that this feature in Yocto is a little bit specific, because if you switch to read-only rootfs, there are certain applications that may require to write data on first boot. And if the rootfs is read-only, they won't be able to do this on first boot. This is very typical for desktop environments. And to avoid this, you need to provide some kind of a solution with the setup for Mender. One possible solution is to make these applications to write to the data partition, which remains persistent through upgrades and is a read-write partition. Now, about the Toradex Verdin i.MX 8M+. This is a member of the Toradex Verdin family. It's a system on a module with i.MX 8, 4 GB of RAM, 16 GB of storage, Wi-Fi, and Bluetooth. I really like the concept of Toradex and other companies making modules, because the modules are packed together with all the hardware that's required to have the system running. And hardware engineers can focus on creating carrier boards with peripherals for the specific needs of the industrial devices which these modules are controlling. This is saving time and money to go to the market, and it's very convenient, especially for use cases where you're not going to manufacture millions of devices, and modules can be really useful. One very specific thing about Toradex is the so-called Toradex Easy Installer. It comes pre-installed on all the Verdin systems on a module. Now, let me share with you the exact steps how to build simple Poke image with Mender for this hardware. These steps are available in online in Mender resources. We are using Toradex BSP version 6.0. From time to time, Toradex are releasing new BSPs. These BSPs match specific Yocto release. And the steps that I'm showing you here are for the latest long-term support release of the Yocto project, Kirkstone. Initially, because this particular hardware was not supported by Mender, I had to do porting. The porting was quite easy because there was similar hardware, so I needed to make just a few changes. And initially I did them for Dunfell. Later on, everything was ported to Kirkstone, so now you can use Kirkstone. The process is straightforward. Here for this example, I'm using the Google Repo tool to initialize all the layers. After that, I'm initializing the build environment. A few changes are required to local.conf and bblayers.conf. This is pretty much to make sure that we are using the right Toradex BSP version. Also, for demo purposes, we can add the meta-mender demo. However, this, as the name suggests, is only for demonstrations. It shouldn't be used in a product environment. If you have used i.MX 6 or i.MX 8 devices with the Yocto project and Open Embedded, you know that to use all the hardware features, you need to accept the Freescale end user agreement. So this line has to be added to conflocal.conf. And something specific that should be configured for the Verdin i.MX 8M+. These are Mender-specific variables, which are provided through the meta-mender layers. Basically, we're specifying the location of U-boot and the storage device on which we have the A and B partitions, so that Mender will know and the bootloader will know how to switch between them. And finally, we're ready to kick off a build. Here, for example, I'm building core image Western. At the end, we have two important artifacts. The first one is the .mender file. This file is used to perform the update, and the other file is the mender_tesi tar file, which is an archive that we will provide a Toradex Easy Installer for initial installation. And here we come to something that's very specific for Toradex devices. This is the Toradex Easy Installer, a Linux-based application with graphical user interface for installation images on the internal flash memory of the system of modules. It could work with a USB stick or over the network. I have to say that although it's quite convenient for users who are used to hook up a monitor, keyboard, and a mouse, it's not so convenient if you are a user used to work in a terminal. However, the Toradex Easy Installer has a lot of advanced features, including automatic installation. There are options for pre-install, post-install script hooks, so you can automate pretty much the whole process. So in order to take advantage of the automatic installation, you need to set up this variable in local.conf to true. This is something that's coming from the Toradex BSP layers. For my own need, I'm using the Toradex Easy Installer with zero configuration. This helps me to automate the installation process. So here I have shared some information how to use Zeroconf so that Toradex Easy Installer can automatically find appropriate images which are shared on a computer in the same network. So how does this all work? We have several important BSP layers. We have the meta-Toradex NXP layer. Meta-mender is providing, of course, the mender recipes. And we have meta-mender-Toradex NXP, which is coming from meta-mender community. It's a sublayer. Meta-mender-Toradex NXP is where the integration of new devices happens. So if you need to port Mender to a new device that's not supported as of the moment, you most probably need to go to meta-mender community and find an appropriate sublayer for depending on the hardware to which you are porting it. In the particular example for i.MX 8MP and the Verdin module, I had to do a little bit of work. I would say it was not even that advanced. It was more like intermediate work because a meta-mender community is very well maintained. There are a lot of devices already there, and just a few changes are needed in most of the cases to add a new device within the same family. And here is a screenshot of the U-boot files and the different patches that we have for the different supported Toradex machines. As you can see, we have i.MX 6 and i.MX 8 machines by Toradex, which are supported for meta-mender community and meta-mender-Toradex NXP. So if you're porting Mender to a new Toradex system on a module, or in general to a new device, you have to use meta-mender community. For Toradex specifically, the BSP is meta-Toradex NXP. The changes, as I explained, has to be applied through meta-mender-Toradex NXP. There's a checklist of tests that has to be performed. This is the so-called Mender integration checklist. It's available online as part of the documentation of Mender. By the way, Mender is having a pretty good documentation. And finally, you have to share the exact steps how to build a demo image in the Mender hub. So this is pretty much it. Let's wrap it up with a few conclusions. I have to say Mender is a very reliable turnkey end-to-end solution for software updates of embedded Linux devices. It's featuring both client application and a server. Mender is available as a free open source software for AB updates, and there are paid commercial plans for doing the Delta updates, which I briefly explained in the previous slides. There are numerous board integrations in meta-mender community, including for the Toradex systems on a module, which are in meta-mender-Toradex NXP. Something specific for Toradex is the Toradex Easy Installer. As usual, contributions are always welcome. I have to say that the maintainers are very friendly, and they are helping people interested in porting Mender to new devices. Thank you very much. This is the last slide, but last but not least, I would say big thanks to the maintainers, Drew Mosley, who's looking after the meta-mender Toradex layers, and Joseph, who's also doing maintenance of the meta-mender layers. And I think we have a few minutes for questions, so I'll be happy to hear them.